Hi, this is Dr. Goldstein, and today I am going to discuss logarithmic differentiation. So I'm going to do that by showing you two different examples. In the example on the left, I want to use logarithmic differentiation because it's going to make taking this very, very complicated derivative much easier. In the example on the right, I have a variable in both the exponent and the base of this function. So in this example, I don't have any derivative rules that I can use. So again, the first example is complicated, but it's made easier with logarithmic differentiation. And in the second example, I actually need to use logarithmic differentiation because no other derivative rules apply. In particular, I want to point out that taking the derivative of this as x times x to the x minus 1, this is very bad. Because you can only use this rule when you have a number in the exponent and not when you have a variable in the exponent. Okay, so let's actually see what we can do with logarithmic differentiation for these two examples. So logarithmic differentiation begins by taking the natural log of both sides. So I'm going to take the natural log of y on the left-hand side of the equation, and I'm also going to take the natural log of the right-hand side of this equation. So the natural log of 2 to the x plus the square root of x cubed minus 1 divided by the square root of x times 2x minus 1. Now what I can do, because on the right-hand side I have a logarithm, is I can split this up using logarithm rules. For starters, I have a fraction, so I can write this as the natural log of 2 to the x times the square root of x cubed minus 1 minus the natural log of the square root of x times 2x minus 1. And now I can keep going. So not only do I have a fraction, but I have things that are being multiplied together, and so I can add them inside of separate logarithms instead of multiplying. So this is the natural log of 2 to the x plus the natural log of the square root of x cubed minus 1 minus the natural log of the square root of x. And now I have to distribute this minus sign to both of these terms, the natural log of 2x minus 1. Now the last thing that I'm going to do is I'm going to remember that square roots are things raised to the 1/2 power. So I'm going to bring that power down front of my logarithm, and I'm also going to bring this x out of the exponent in my first term. So I'm going to write this as x times the natural log of 2 plus 1/2 natural log x cubed minus 1 minus 1/2 the natural log of x plus, in this term, oops, I forgot to distribute my minus. I was very careful in the last step, minus the natural log of 2x minus 1. And this is as much as I can expand my function. Now remember, I haven't changed the other side of this equation. I still have that this is the natural log of y. And notice I haven't taken any derivatives yet. I took the natural log of both sides, and then I just expanded this really complicated thing. But I haven't actually taken any derivatives. So now I am actually going to take the derivative of both sides of this. So I'm going to take the derivative of the left-hand side and the derivative of the right-hand side. Now, let's start with the right-hand side. The natural log of 2 is a number, so when I have x times the natural log of 2, its derivative is just natural log of 2. Now, in my second term, I still have to use the chain rule, but I only have to use it once instead of twice. I have my 1/2, and I have the natural log of x cubed minus 1, and so its derivative is 1 over x cubed minus 1 times 3x squared. In my next term, I have this 1/2, and then the derivative of the natural log of x is just 1 over x. And in my last term, I have 1 over 2x minus 1, and then the chain rule gives me an extra 2. So that's the right-hand side. On the left-hand side, remember that y is a function of x, so I have to use the chain rule on the left-hand side. So here, y is a function of x, so I have to use the chain rule. And I end up getting 1 over y times, you can either write this as dy dx or just y prime, the derivative of y. So now I'm done taking my derivative, and I'm actually just going to draw a line here, because now I took the derivative. And I want to separate my work from before taking the derivative and after taking the derivative. Just because when I look at it, I know exactly what I'm doing. So, what did we want to do in this problem? We wanted to find the derivative of y equals 2 to the x root x cubed minus 1 divided by root x times 2x minus 1. We wanted to find y prime. Well, we have it now. We just have to solve for it. So, I'm going to solve for y prime by multiplying both sides of my equation by y. So multiplying by y, we have that y prime is equal to y times the natural log of 2 plus, and I'll simplify this a little bit, 3x squared divided by 2 times x cubed minus 1 minus 1 over 2x minus 2 divided by 2x minus 1. And the last thing that I want to do is I don't really want a y on the right-hand side of this equation. I want a function of x. So I go back to the beginning and I say, oh, hey, what was y? Y was that expression. And so I use that to replace y. And so all in all, I have 2 to the x times the square root of x cubed minus 1 divided by the square root of x times 2x minus 1. All of that times natural log of 2 plus 3x squared divided by 2 times x cubed minus 1 minus 1 over 2x minus 2 over 2x minus 1. And that's my final answer. Now, this may seem ridiculously complicated, and it is complicated. This is not an easy example. But remember what we would have to do to take the derivative of this original expression. We would first need to use the quotient rule. And then we would need to use the product rule when taking the derivative of both the top and the bottom. And then, while we're using the product rule, we have a chain rule as well. So we would have a chain rule within the product rule. So we have a chain rule in two different product rules in the quotient rule. Yuck. So this is why, for this function, using logarithmic differentiation is worth our time. Because at this step when we take the derivatives themselves are fairly simple. We have more symbols to work with because we've expanded everything, but each individual derivative is much simpler. Okay, let's move on to an example where we have to use logarithmic differentiation. So again, in this example, I have a variable in the base and in the exponent, so I must use logarithmic differentiation. I have no other method that I can use. None of my derivative rules apply. So again, I take the natural log of both sides of this equation, and then I simplify the right-hand side of this equation. And in this case, the only thing that I can do is bring down the exponent. At this point, I take the derivative. On the right-hand side, I have to use the product rule. So when I take the derivative of x, I get 1, and that gets multiplied by the natural log of x. And then in my next term, I have x times the derivative of the natural logarithm, so times 1 over x. And again, on the left-hand side, I have the natural log of y, and y is a function, so I have to use the chain rule, and I get 1 over y times y prime. In my next step, I solve for y prime by multiplying both sides of my equation by y. And while I'm at it, I'm going to simplify the derivative that I just took. So I get the natural log of x plus, both of those x's cancel out, so I get the natural log of x plus 1. And now the last thing that I want to do is rewrite this just in terms of x. So I take the expression y equals x to the x that I started with, and I use it to replace y. So now I have x raised to the x power times the natural log of x plus 1. And it's perfectly fine to just leave that expression like that. So let's summarize this method. The first thing that we do is we write y equals f of x, and we take the natural logarithm of both sides. So in our previous example, this got us to the point of writing the natural log of y equals the natural log of x raised to the x. The second thing that we do is we expand the right-hand side. We expand the natural log of f of x in order to make taking the derivative easier. So in terms of our last example, we had the natural log of y equals x times the natural log of x. The next thing that we do once we're done expanding is we take the derivative using the chain rule for y. And so in our last example, we had 1 over y times y prime equals the natural log of x plus 1. And then the last step is to solve for y prime, which at the beginning of this problem is what you wanted to calculate. So in order to do that, we have y prime equals y times the natural log of x plus 1. And then you replace your original expression y. You have x to the x times the natural log of x plus 1. And at the end of that step, you are done calculating y prime. You are done calculating the original derivative that you wanted to find.